Okay, so hopefully it's becoming relatively apparent that Liouville space is just like Hilbert space, where the Liouvillean kind of plays the role of the Hamiltonian in Hilbert space. All right, so what we're going to do now is we're going to work out the situation when the Hamiltonian does depend on time. Okay, so when the Hamiltonian does depend on time, the idea is relatively straightforward, because now when we write down the derivative, the time derivative, we write down the time derivative of the time evolution operator. Right? We'll have minus I over h bar L of t now, u of t naught. Okay, and so because we know what happens here, we already know the answer to this. We worked it completely out for the case of Hilbert space and the Hamiltonian. All right? So that means we know automatically that t, the time evolution operator, is a time-ordered exponential like this. Okay, this is something we already know. We can write down the series expansion of this if you like. It has the same exact form. Right, so it's over here. It's 1 plus the sum of n equals 1 to infinity minus I over h bar to the n, and then all these integrals. And now instead of these integrals having h in them, the integrals have L. All right, so that's what we mean when we say the time-ordered exponential operator. It's the same exact thing. Now we can ask ourselves, what does u operating on rho do? Right, because that's sort of what we're interested in. So let's do that. So u t naught operating on rho of t naught. Why do we care about this? We care about this because this is how we get our system to be evolved in time. Last time we looked at this and we saw that this gives us the commutator when you convert it back into Hilbert space. So we're allowed to go back and forth between the spaces however we want, right? It's basically just repacking the matrix. We took the density operator, we made it into a vector. So by stretching it essentially, pulling the elements apart, then we converted the Liouville equation, which was the commutator, into that one multiplication by that big operator, the Liouvillean operator. So we can do the same thing here. If we put this inside, we're going to have rho of t naught plus this sum times the integrals. This is an n here, of course. Right, and then remember we're going to have L, all the different L's operating on it down to rho. Okay, so that means what that's going to look like when we do this is going to be a bunch of commutators. Now, this is going to look really weird. You probably have not seen anything remotely like this before. So we're going to go through this slowly with like sort of hand-drawn examples as much as possible. Because now we have this nested commutators. And why is that? So let's think about what one application of L does, right? So L of tau 1 on rho of t naught. When we convert this back into Hilbert space, right, this is going to be L operating on rho of t naught, but it's L at tau 1. Well, that's equal to h of tau 1 commutator with rho of t naught. So that's, h tau 1 rho t naught minus rho of t naught h of tau 1. Right? It's nothing magical about that. This is how you go from this expression in Liouville space to this expression in Hilbert space. Now let's look at what happens when we do L tau 2 L tau 1 rho t naught. All right, well, we just did this piece a second ago. So now what we have is L tau 2 on this whole thing, which is this commutator, which we don't need to write out again. All right, so it's going to be this times this minus this times this. That's going to look like, so that's going to be, when we write it with the Hamiltonian, of course, is what I mean to say. So h tau 2, the commutator with this. That's what we mean when we say L times something, L operating on something. It means commute the Hamiltonian with it. So we're doing the commutator of h with this. All right, so that's just two terms. And if you keep going and going and going, you get a formula that looks like this. Here are the two terms I just did, and you can just keep going. All right, so when you see this expression written as Liouville space, you can convert it back into Hilbert space just by remembering what the Liouvillean operator becomes. It becomes this commutator operator in Hilbert space. All right, for completeness, and if you're a masochist, or if you just like being super careful, then you might ask, what about U dagger? Not T, U dagger. Well, just like everything else, when you dagger it, you kind of like switch things around, switch the order. If there's an I, you might make a minus I. So this is just going to be the negative time ordered exponential operator with a plus I over h bar. T naught to t d tau L tau. And I don't remember if I derived what to do with U dagger in the case of the Hilbert space, but you do the same thing. You write the Schrodinger equation for U dagger, do this iterative substitution, and you just change the order of all the sequence of the operators. Instead of going from T1 or tau 1, tau 2, tau 3, they go tau 1, tau 2, tau 3, they go the other way. All right, so now what we're going to do, you're probably following along here, is we're going to introduce the interaction picture. So to do the interaction picture, all we need is two pieces of Hamiltonian. Obviously, we're thinking ahead to molecule and field, but it doesn't have to be thought of in that way. Just any two pieces that you can break it into. And then the idea, of course, is if you have an H and an H prime, then you can come up with the L and L prime. So the Liouvillean will be an L naught part plus L primed. Right? In direct analogy, right? And it's not even really an analogy, right? This is just, we're saying that this is. So what does L do? So L, for example, of T operating on something, if we convert back into Hilbert space, so I might put an arrow there, is going to be the commutator of H with A, right? So L naught will be this. L primed, same deal. H primed. All right, that should be reasonably clear, hopefully. So now, since we know that there's an isomorphism between the U in Liouville space and the regular U in Hilbert space, we can just go back to our notes where we derived everything, the Dyson series, and switch all the little u, the curly u's, the regular u's to curly u's, right? All the h's to l's, and we'll end up with a directly equivalent expression for the time evolution operator being this one, right? U naught of t naught times ui t naught. Okay, and what's ui? It's what you think it is. It's the time-ordered exponential operator minus I of h bar t naught to t d tau of L primed tau. L primed I tau. Right? What's Li? L primed I, let's say. Right? That's U naught dagger on L primed. U naught not dagger. So it's that same kind of transformation that we did originally in Hilbert space to the operators to make them interaction picture operators. All right. So what that tells us then is that the time evolution operator, whoops, in Liouville space can be written exactly as this. A time evolution operator for the L naught Liouvillean times this positively time-ordered exponential operator this might get cut off. So this is d tau L primed I of tau. Okay, so it looks exactly like what it did when we were in Hilbert space. And there's a reason for that. It's really just because we have two different linear spaces and we made an isomorphism between the two of them. That means there's like a one-to-one correspondence between every object in the Hilbert space with every object in Liouville space. The last thing that we're going to do here in this section that we need to put together is just write this out, right? What is this? We are going to assume we know the Hamiltonian H naught and its eigenvectors. That's like the system. Then we're going to write this out and truncate it after some term. That's the basic strategy. All right, so U is U naught. That's from the one term, wherever it is, somewhere up here, there. All right, plus remember the cool trick that we did, right? It was to realize that when we write this term out, we're going to have this product of L, and then we're going to have, when we write down the interaction picture, we're going to have these U daggers and U naughts, the U's and U daggers, U naughts and U naught daggers, but they're all going to have these different times from 0 to tau 1, from 0 to tau 2, 0 to tau 3, and so on. And we'll use that same trick to cut them in between, like exactly the same that we did for the Hilbert space version of all this. So that's our sort of integral structure, and then I'll write down the thing below it. Right, so this is going to be U naught t tau n. And the last bit here was just the trick of bringing the U naught in, because the t and the t naught don't depend on, are not variables of integration for any of these. They happen to be the limits, but that's it. So they can come in. And then we convert back from the interaction picture to the non-interaction picture, whatever you want to call it. The Schrodinger picture in Liouville space if you want. This is going to be tau n minus 1, right? And then I'll put a couple terms in just for the heck of it. Tau n minus 1, and so on, all the way down to the last couple terms. So U naught tau 2, tau 1, L primed, tau 1, U naught, tau 1, and T naught. All right, and the interpretation of this is identical to the interpretation that we had when we did this in Hilbert space. Let's call the H naught part or the L naught part, the field-free evolution, whatever the system would do by itself with given a density operator that you have, or a state. This is the field-free. Then we hit it with whatever the interaction is, the field, right? Then it's free again, then the field, then free, then field, then free, and then we add up all these different time-ordered combinations of these things, right? And that's what we're doing when we're doing perturbation theory. We cut it at some low order. Okay, now we can actually sort of stop here. We could, I'm not going to, but we could stop here. This equation is an important one. It's 358 in the Mukamel book. And the nice thing about it, of course it wasn't a coincidence, the way that Professor Mukamel numbered his equations, cleverly, equation 258 is the Hilbert space version of this. So you can have those two chapters, 2 and 3, right next to each other, and they're like the Rosetta Stone for how to go between Hilbert space and Liouville space. Okay, so that's 358. So if you want to follow along, for our class I put the chapter 3 up, but probably you can get access to the Mukamel book without any trouble. It's a good book to look at. There are other derivations of all of this stuff. Some of the derivations I've done have come from the Messiah textbook, which is rather old, but still pretty rigorous. I like it. But you can find equivalent kinds of things in other textbooks. What's nice about the Mukamel book is it's developing the quantum mechanical formalism with the specific intent of getting to the optical response functions. You're not going to find that in a standard quantum mechanics textbook. All right. So what we want to do now is we want to think a little bit about how we can write down some notations that are going to be useful for when we have systems that have, molecular part, let's say, and a field part. So the way we start with this is we start from the beginning. We start with the Liouville equation. We're going to break the Hamiltonian into two pieces. So we're going to call it H naught plus an interaction, H primed of T. Okay, so then we write down the equation again. We're going to have H naught plus H primed, commuting with the commutator with P, with rho, rho of T. So when you write this out, you're going to have this times this minus this times this. Right, that's going to give you sort of two terms, right? You can convince yourself that of these sort of identities of commutators, right? So one of them is going to be H naught and rho. These are all linear things. Right? So we have these two separate commutators. One involves H naught, the other one involves H primed. So now, using this as a springboard, we can switch ourselves back into Liouville space, right? Because we know that rho dot is going to equal minus I over H bar, L naught, rho of T, minus I over H bar, L primed of T, rho of T. Now, am I using all the notation here? No, right. I should be putting these arrows on. But that you understand, hopefully, that's what's going on. These are Liouville space vectors. And that's the time derivative of a Liouville space vector. Okay, so what we can do now is we can put in a little bit of notation. So one of the things that we can do is put in notation, for example, that we might want to know, what does this L do? L primed, right? So L primed is going to be in Hilbert space. L primed on anything will be in Hilbert space L primed on A, right? That'll be equal to H primed, the commutator with A, right? These things depend on T. So I could call H primed V if I want. In the Mukamel book, he switches to V at this point. So then if I go backwards, I would call a Liouville operator. I could have a Liouville operator, say V, operating on A, will correspond to the Hamiltonian associated with V. So this would be corresponding to V commutator with A. Okay? So what the reason for doing this is just going to be to help convert some notation, number one. And number two, we're going to think a little bit about this step in between, all right, that I probably didn't explain in the past in this way. So one thing that we're going to do is we're going to use the U-0 part of the Hamiltonian. So this would work both in Hilbert space and in Liouville space, right? And the idea is, what is this? This is going to be some exponential, right? E, so minus I over H bar H0, T minus T0. And this will be L0. Right? Because the Hamiltonian for the naught part is time independent. So what we can do is we can convert this time difference, right, into a function that is off and then turns on at a particular time. Right, so we're going to say, you know, before nothing happens and all of a sudden we turn it on. And the way we can do that then is we simply multiply this time evolution operator by something called the Heaviside function. All right, the Heaviside function, T minus T0, for example, will be 1 when T is greater than T0, and it'll be 0 when it's before. Okay, and so we simply introduce a new notation, which we can write in Hilbert space in this way. Will be I'm out of space here. And it will be in Liouville space this. All right, so what these are called are so-called Green's functions. And they're named after a mathematician who was, I think, a school teacher, Green, who first used them in math. We have two words for them that people tend to use somewhat interchangeably, especially in the case of time evolution. So Green's functions come up anytime you have a perturbative series like this. They don't have to be for the time. They could be for number of particles, for example. So that's where it shows up a lot of times in some electronic structure theory. In time-dependent perturbation theory, the Green's function is also called a propagator. It propagates the system in time. Okay. We also call it time evolution operator. So we can rewrite all of our equations using Green's functions instead of these U's. And so we'll do that just because that's the way The Mukamel textbook does it, and you'll see other textbooks that do it too. You can always go back to this. There's nothing wrong about this. It's just a different terminology. There's a few reasons why it's nice to use Green's functions, particularly if you are interested in switching between the time domain and the frequency domain. There are some transformations that will automatically be obvious when you realize these are Green's functions that might not be super as obvious when they aren't having to do with integrals in the complex plane. All right, so we're going to stop there for now and pick this back up as we essentially work towards the optical response functions.